Good morning. The chapter for today is The Language of Chemistry. Let's see the subheadings of this chapter. This chapter is divided into two parts. The first one being symbol of an element, valency, formula of radicals and formulae of compounds, balancing of simple equations. We have subdivisions like symbol, valency, radicals, compound, and chemical equation. The second part of the chapter is relative atomic masses, that is atomic weights, and relative molecular masses, that is molecular weights, either standard H atom or 1/12 of the carbon 12 atom. In that we have definitions and calculation of relative molecular mass and percentage composition of a compound. Introduction. Chemistry is a branch of science in which we study about matter, like what is matter made up of, what is its nature, structure, and what changes are observed when it is subjected to different conditions. The basic units of matter in any state is considered as molecules. This is because a molecule is the smallest particle of matter which is capable of independent existence. A pure substance is one which is made up of molecules containing the same kind of atoms. For example, carbon dioxide gas is pure substance. A molecule may contain similar atoms or dissimilar atoms. A pure substance in which a molecule is made up of atoms of same kind is called an element. So we define an element as a simple and pure form of matter which cannot be decomposed into simpler substances. All elements are made up of atoms, the smaller particles of an element, which represent all the properties of an element. An atom is the smallest particle of an element which may not exist independently but can take part in chemical reaction. Atomicity is the number of atoms in a molecule of an element. Let's see what molecules can be divided into: monoatomic, diatomic, and even polyatomic. Monoatomic molecules, elements having only one atom in their molecule. Examples are noble gases like helium, neon, argon, krypton, and xenon. Diatomic molecules, elements having two atoms in their molecules. Example is hydrogen, oxygen, nitrogen. Triatomic molecules, elements having three atoms in their molecules. Example, ozone. Tetraatomic molecules, elements having four atoms in their molecules. Example is phosphorus. Octatomic molecules, elements having 8 atoms in their molecules. Example is sulfur. A molecule is the smallest particle that has a capability to exist independently. Before 1600 AD, alchemists used pictographic symbols. Then Dalton used other types of symbols. Later, John Jacob Berlioz used initial letter of an element in capitals. The symbols were based on Latin names or other language names of the elements. The method suggested by John Jacob laid the basis of the IUPAC, which is International Union of Pure and Applied Chemistry. Let's see the table below, which shows elements with their Latin names. Gold, symbol is AU, Latin name is aurum. Silver, symbol is Ag, Latin name argentum. Mercury, Hg, which is hydrargyrum. Copper, Cu, cuprum. Lead, Pb, plumbum. Iron, Fe, ferrum. Sodium, Na, natrium. Potassium, K, kalium. Tin, Sn, stannum. Antimony, Sb, stibium. Tungsten, W, wolfram. Symbols. A symbol is a short form that stands for atom of a specific element or the abbreviation used for the name of an element. Each element is denoted by a symbol which is usually the first letter of its name in English or Latin written in capital. Example: sulfur, an element, is denoted by the symbol S. However, when first letter of more than one element is the same, the elements are denoted by two letters. The first letter is written in capital while the second one is written in small. Example: carbon, cobalt, copper, calcium, cadmium, chromium, and chlorine are elements whose first letter is C. Therefore, only carbon is denoted by symbol C. Cobalt is denoted by two letters CO. Copper is denoted by two letters Cu, taken from Latin name cuprum, and so on. Significance of a symbol. It represents the name of an element, one atom of the element, a definite mass of element that is equal to atomic mass expressed in grams. For example, the symbol N stands for the element nitrogen, one atom of nitrogen, and 14 grams of nitrogen, this weight being the atomic weight of the element. Symbols of some common elements are given in the table below, with first column being the name in English and the second column is symbol. Valency. The valency of an element is the measure of its combining power with other elements. Valency is measured in terms of hydrogen atoms or oxygen atoms. It is a number of hydrogen atoms or double the number of oxygen atoms that can combine with it. Since no other element has combining capacity less than that of hydrogen, its valency is taken to be 1 and is considered a standard. Modern definition of valency. The number of electrons that an atom can lose, gain, or share during a chemical reaction is called its valency. Electrons in the outermost shell of an atom are known as valence electrons. An atom contains electrons, protons, and neutrons. Each electron has one negative charge and each proton has one unit positive charge. Neutron has no electric charge, it is neutral. Every atom normally contains an equal number of electrons and protons which balance the charges in the atom and make an atom electrically neutral. An ion is a positively or negatively charged atom for group of atoms which is formed by loss or gain of electron by an atom or group of atoms. As we have already seen, an ion is a positively or negatively charged atom or group of atoms which is formed by loss or gain of electrons by an atom or group of atoms. The loss or gain of electrons in an atom depends upon electrons in the outermost shell. To attain stability, atoms have to have 8 electrons in their outermost shell. Thus, atoms with 1, 2, or 3 in their valence shell lose these electrons to attain stability and thus form monovalent or univalent, divalent, and trivalent positive ions respectively. Positive ions are known as cations. The below picture represents monovalent, divalent, and trivalent. Elements with 1, 2, or 3 electrons in their outermost shell, that is valence shell, are usually metals. Out of the elements that have 4 electrons in the outermost orbit, carbon is a nonmetal. Silicon and germanium are metalloids and rest are metals. Elements with 5, 6, or 7 electrons in their outermost shell are normally nonmetals. Atoms with 7, 6, and 5 electrons in their valence shell gain 1, 2, or 3 electrons respectively in order to complete their octet, and thus they form monovalent or univalent, divalent, and trivalent negative ions. Negative ions are also known as anions. The below picture represents the monovalent, divalent, and trivalent. In the table below, we'll see the number of electrons in the outermost shell with their valency. Valency is the combining capacity of an atom or of radical. The valency of an element or of a radical is the number of hydrogen atoms that will combine with or displace one atom of that element or radical. Let's see some examples of sharing of atoms. One atom of chlorine combines with one hydrogen atom to form a molecule of hydrogen chloride. So the valency of chlorine is 1. One atom of oxygen combines with two atoms of hydrogen to form a molecule of water. So the valency of oxygen is 2. In an ammonia molecule, one atom of nitrogen combines with three atoms of hydrogen. So the valency of nitrogen is 3. In methane molecule, one carbon atom combines with four hydrogen atoms. So the valency of carbon is 4. Variable valency. Certain elements exhibit more than one valency, that is, they show variable valency. Reasons for variable valency. An atom of an element can sometimes lose more electrons than are present in its valence shell. That is, there is loss of electrons from the penultimate shell too. Therefore, such an element is said to exhibit variable valency. If an element exhibits two different positive valencies, then we use suffix OUS for the lower valency and suffix IC for the higher valency. Modern chemists use Roman numerals in place of these trivial names. For example, stannous chloride, which is SnCl2, is written as tin and Roman number 2 chloride, and stannic chloride is written as tin Roman number 4 is SnCl4. Non-metals like nitrogen, phosphorus and sulfur also show variable valency. Nitrogen and phosphorus exhibit valencies of 3 and 5, while sulfur exhibits valencies of 2, 4 and 6. In the table below, we have some examples of variable valency for iron, copper, mercury, lead and tin. Formula. Atoms of elements combine to form molecules. The symbolic representation of molecule is known as formula or molecular formula. A molecular formula is also known as chemical formula, which employs symbols to denote the molecule of an element or of a compound. A molecule of an element may contain one or more atoms of it. For example, a molecule of elements hydrogen, oxygen and nitrogen, bromine, iodine, chlorine contains two atoms and are written as H2O2, N2, Cl2, Br2 and I2 respectively. In case of compound, the molecule containing different atoms united in certain fixed ratio is represented by placing symbols of elements present in it side by side, indicating their numbers written in subscripts. Thus, NH4Cl represents one molecule of ammonium chloride containing one atom of nitrogen, 4 atoms of hydrogen and 1 atom of chlorine. Na2CO3 denotes one molecule of sodium carbonate which contains 2 atoms of sodium, 1 atom of carbon and 3 atoms of oxygen. H2O represents 2 molecules of water, that is dihydrogen oxide. Each molecule contains 2 atoms of hydrogen and 1 atom of oxygen. By looking at the formula, we understand the ratio in which different atoms are united to form the molecules. Let's understand the significance of molecular formula. Molecular formula of a compound has quantitative significance. It represents both the molecule and molecular mass of the compound, the respective numbers of different atoms present in one molecule of the compound, the ratios of respective masses of elements present in the compound. For example, the formula of CO2 means that molecular formula of carbon dioxide is CO2. Each molecule contains one carbon atom joined by chemical bonds with 2 oxygen atoms. The molecular mass of carbon dioxide is 44. Given that the atomic mass of carbon is 12 and that of oxygen is 16. Radicals. The molecule of a compound is usually made up of 2 parts, These parts separately are known as radicals. Let's take the example of molecule potassium chloride, which has two parts, potassium and chloride. So potassium is one radical and chloride is the other radical. So a radical is an atom or a group of atoms of the same or different elements that behave as a single unit with a positive or negative charge. A radical is called simple radical when it is an atom only like sodium, which is denoted by Na+, and magnesium Mg2+. It is known as compound radical when it is made up of group of two or more different atoms, that is polyatomic like sulfate SO4, made up of one of the sulfur atom and four oxygen atoms. Note, an acid reacts with base to produce salt and water as a result of neutralization. So potassium hydroxide, which is a base, plus hydrochloric acid gives potassium chloride, salt plus water. In the formation of potassium chloride, the potassium radical has been contributed by the base potassium hydroxide and is therefore called basic radical. The chloride radical has been contributed by hydrochloric acid and is therefore termed as acid radical. When a salt is dissolved in water, it splits up into constituent radicals. The basic radicals are found to carry positive charge and so are termed as electropositive radicals or cations. The other part carries negative charge and so are called electronegative radicals or anions. Thus, in potassium chloride, potassium is electropositive and chloride is electronegative radical. Similarly, in the magnesium sulfate, magnesium is electropositive and sulfate is electronegative radical. In this slide, we see a table with list of some common electrovalent positive ions, that is basic radicals. This slide contains a table with list of some common electrovalent negative ions, that is acid radicals. Writing the chemical formulae. The following steps should be taken while attempting to write a formula. This method is called the crisscross method. Write the symbols side by side. Basic radical is written first and then acidic radical. Write the valency of each atom on the top of its symbol. Ignore the plus or minus symbols of the radicals. Divide the valency numbers by their highest common factor or HCF, if any, to get the simplest ratio. Interchange the valencies of the radicals. Write the interchanged valency numbers to the lower right of the radical. If the radical is a group of atoms and has a valency number more than 1, enclose it with parentheses. There's a table based on the steps mentioned along. The formula can be written in the following way. Name of the compound, symbols with valency and charge, exchange of valency and formula. The compounds here are magnesium chloride, calcium oxide, aluminum hydroxide, ferric oxide, sodium metaaluminate, sodium aluminate. This slide contains some important formulae. You have chemical name, symbol with charge, and formula for your reference. The following slide also has some important formulae with chemical name, symbol with charge, formula for the reference. Naming certain compounds, a metal and a non-metal. The metal is written first, followed by non-metal, and the suffix IDE is added to the non-metal. For example, calcium plus nitrogen gives calcium nitride, Ca3N2. Two non-metals, the prefix tri or tetra or penta, etc. is added as the case may be to the second non-metal. For example, PCl3 is phosphorus trichloride and PCl5 is phosphorus pentachloride. Two elements and oxygen. Oxygen is represented at the end of the formula. The name of the compound depends on the number of oxygen atoms present in the compound. The prefix hypo is used if the number of oxygen atoms is less than 2. And suffix ite is used if the number of oxygen atoms is 2. The suffix ate is used if the number of oxygen atoms is 3, and the prefix per is used when the number of oxygen atoms is more than 3. Naming of acids. The names of binary acids are given by adding the prefix hydro and suffix ic to the name of the second element. Examples are hydrochloric acid is HCl. Names of the acids containing radicals of polyatomic groups are given on the basis of second element present in the molecule, and prefix hydro is not used. Examples: H2SO4, the second element is sulfur, hence the name sulfuric acid. If the number of oxygen atoms is less than suffix, OUS is added instead of IC. Thus, H2SO3 is sulfurous acid. HNO2 is nitrous acid. Trivial names. They are certain compounds with names that do not follow any systematic rule. Such names are called trivial or common names. They are widely accepted. Example: nitrogen trihydride is called ammonia. Hydrogen monoxide or dihydrogen oxide is called water. To calculate the valency from the formula, the valency of elements can be determined based on the knowledge of the valencies of radicals and of the fact that valency of hydrogen H is equals to 1, oxygen O is 2, chlorine Cl is 1. In the table below, you will find the procedure to find the valency with the example. The procedure is: write the given formula, interchange the subscript and write it as superscript. The valency of oxygen is taken as 2, therefore multiply with superscripts by 2. The result gives the valency of the elements. Thus, from the formula NO3, we find the valency of nitrogen is 4. Let's know what a chemical equation is. A chemical equation is a symbolic representation of chemical reaction using the symbols and formulae of the substances involved in the reaction. For example, burning of coal in air is a chemical reaction in which a new substance, carbon dioxide, is formed. The reaction can be represented either by a word equation or chemical equation. Steps involved in writing a chemical equation. Write the symbols or the formula of the reactants on the left hand side with plus sign between them. Write the symbols or the formula of the products on the right hand side with plus sign between them. Put the sign of an arrow in between the reactant side and the product side. Represent the reactants and products in their molecular forms because their atomic forms are usually neither stable nor capable of separate existence. Let's take the example of sodium. Sodium reacts with water to form sodium hydroxide plus hydrogen. Its 2Na2 plus 2H2O gives 2NaOH plus H2. A chemical equation tells us what substances are involved in a given reaction, that is reactants, and what substances formed as a result of reaction, that is products. In the example, CuSO4 plus 2NaOH gives CuOH2 plus Na2SO4. In the given equation, copper sulfate and sodium hydroxide are reactants which react to produce copper hydroxide and sodium sulfate, which are products. Chemical reactions may involve one reactant and two or more products, two reactants and one product, two reactants and two products, two reactants and three or more products. Skeleton equation. It is an equation that represents a chemical change but is unbalanced. In other words, the total number of atoms of each element on the two sides are not equal. The following example will make the point clear. KNO3 gives KNO2 plus O2. In the above chemical equation, the number of oxygen atoms in the reactant, which is KNO3, on the left hand side is not equal to the number of oxygen atoms in the product form, that is KNO2 plus O2 on the right hand side. Balanced equation. It is an equation in which the total number of atoms of each element in the reactants on the left side of the equation is same as the number of atoms in the products formed on the right side of the equation. Example, CaCO3 gives CaO plus CO2. This equation, the number of atoms of Ca and CO on both sides is the same. That is, equation is balanced. Let's see another example. KNO3 gives KNO2 plus O2. In this equation, since the number of atoms of oxygen on both sides is not the same, the equation is not balanced. So the balanced form of equation is 2KNO3 gives 2KNO2 plus O2. Why should an equation be balanced? An equation must be balanced in order to comply with the law of conservation of matter, which states that matter is neither created nor destroyed in the course of a chemical reaction. An unbalanced equation would imply that atoms have been created or destroyed. How to balance a chemical equation? There are two methods of balancing an equation: hit and trial method, partial equation method. Let's see the first method, hit and trial method. This method consists of counting the number of atoms of each element on both sides and trying to equalize them. Take the following steps. Count the number of times, that is frequency, an element occurs on either side. The element with least frequency of occurrence is balanced first. When two or more elements have the same frequency, the metallic element is balanced first. The hit and trial method is very useful for balancing simple chemical equations, but it has some limitation, like it takes time to balance complicated equations. The mechanisms or steps of reaction are not very clear. The second one is balancing by partial equation method. Balancing can be done more easily by supposing the complex reaction to have taken the place in the steps. Write the equation for these individual steps and then add the equations. This method is known as balancing by partial equation method. Let's see the limitations of a chemical equation. A chemical equation does not tell us the physical state of reactants and the products, that is, whether the substances are solid, liquid, or gas, the time taken for completion of reaction, whether heat is given out or absorbed during the reaction, the respective concentrations of reactants and the products, the rate at which the reaction proceeds, whether the reaction is reversible or irreversible, whether the reaction is completed or it is not completed. So, a chemical equation can be made more informative by writing the following additional information to it. Information regarding temperature, pressure, catalyst, etc. is provided above or below the arrow, separating reactants and products. The reaction, which are reversible, can be shown by the sign of reversibility. Heating during the reaction can be shown by a sign of delta over the arrow. Physical states of reactants and products can be provided by using letters S for solids, L for liquids, G for gas, upward arrow, and AQ for solution in water. Chemical reactions proceed with evolution or absorption of heat. This information is provided by adding the term heat. Concentration of acids can also be added to the reaction. Any reaction in which precipitation is formed, the precipitate can be represented by downward arrow. Relative atomic mass or atomic weight. Atoms being extremely small cannot be seen or weighed directly, but indirect methods of physics have enabled us to know the absolute mass of nearly all kinds of atoms. The mass of hydrogen atom is found to be 1.66 into 10 to the power of minus 24 grams, while that of carbon atom is 1.9926 into 10 to the power of minus 23 grams. As these masses are too small, it is not convenient to use kilograms or grams as unit. It is therefore been considered appropriate to use the mass of one standard atom as unit and then relate masses of other atoms to it. The resulting masses of atoms are thus known as relative atomic mass, RAM in short form, or atomic weight. In the beginning, the mass of hydrogen atom, hydrogen element being the lightest, was chosen as a unit, and masses of other atoms were compared with it. In 1961, carbon-12 was finally selected because its adoption least affected the values of atomic mass of various elements on the old standard. So the relative atomic mass or atomic weight of an element is the number of times one atom of element is heavier than 1/12 times of the mass of an atom of carbon-12. Thus, the relative atomic mass is equals to mass of one atom of the element by 1/12 of the mass of one carbon-12 atom. Atomic mass is expressed in atomic mass units, that is AMU. Atomic mass unit is defined as 1/12 of the mass of carbon atom C12. The mass of an atom of carbon-12 isotope was given the atomic mass of 12 units. The mass of hydrogen atom is 1 AMU and those of oxygen and helium are 16 AMU and 4 MU respectively. Relative molecular mass or molecular weight. The relative molecular mass or molecular weight of an element or a compound is a number that represents how many times one molecule of substance is heavier than 1/12 of the mass of an atom of carbon-12. The relative molecular mass or RMM is obtained by adding together the relative atomic masses, that is atomic weights, of all various atoms present in a molecule. Thus, the molecular mass of a substance is the sum of atomic masses of constituent atoms present in one molecule of that substance. Percentage composition. Percentage composition of a compound is the percentage by weight of each element present in it. So, percentage of an element in a compound is equals to total weight of an element in one molecule by gram molecular weight of compound into 100. Note, total percentage of all elements in a compound is 100. Empirical formula of a compound. The empirical formula of a compound is the simplest formula which gives the simplest ratio in whole numbers of atoms of different elements present in one molecule of compound. The empirical formula mass is the sum of atomic masses of various elements present in the empirical formula. For example, hydrogen peroxide H2O2. The empirical formula is HO and its empirical formula mass is 1 plus 16, which is 17.